Hello, this is Mr. Champlin. We're going to start looking at our mechanical energy from Chapter 2. First of all, we're going to start with forms of energy. The book we'll be using is written by Jeff Schnick at St. Anselm College. It is found online, so if you need to look for it, you can find it there. Mechanical energy. Mechanical energy comes in two different forms, kinetic and potential. Energy is measured in joules. That's the unit, abbreviated capital J. And kinetic energy is generally called energy due to motion. Potential energy is called energy due to position. There are other forms of energy, thermal, radiant, nuclear, but we will not be analyzing these other forms of energy. Kinetic energy for translational energy, or for translational motion or translational kinetic energy, is the energy of an object moving in a straight line. The formula is right there. 1/2 mv squared. M being the mass, measured in kilograms, and v being the velocity. To simplify how the units work out, you just substitute in the units. So a kilogram goes in for mass, meters per second in for velocity. Then you complete the operation, you end up with kilogram times meter squared over second squared, and that is equivalent to a joule. Up here on the right side, we're going to determine the kinetic energy of the following moving objects. A small bug moving at 10 meters per second, a baseball, a sprinter, and a truck. As you can see in the formula, the velocity has a bigger part, plays a bigger part than the mass, but mass is part of the equation too. So I'll do one completely shown the calculation, and I'll just show you those numbers for the others. Letter A for the bug, KE bug. It's 1/2 mv squared. 1/2 of the mass being 0.010, and velocity 10 squared. If you complete that, it is 0.5 joules. Okay. The others, I won't show you the complete calculation because they're similar. The next one for the baseball. B. KE equals 67.5 joules. For the let's see, sprinter, it is 2,560 joules. And the final one, the truck, KE is 200,000. So you can kind of get a feel of basic energy levels based on the size of the object. But like I said, the velocity is a bigger component of the formula because it's squared. Kinetic energy, rotational. There's also kinetic energy of a rolling object, such as a tire rolling down the rolling or anything else rolling. For the formula, well, the formula first of all for kinetic energy for a rolling object is KE rotational equals 1/2 the moment of inertia, which is I, the symbol is I, and then the next symbol is omega squared. So this is measured in radians per second, rotational unit, radians per second, and I is the moment of inertia. And the units for moment of inertia are kilogram meter squared, and omega is measured in radians per second. Overall, though, you still have the same unit for energy, a joule. Translational motion can be related to rotational motion with the following equation. If you think of a length on a circle, an arc length, S, take the radius of the circle times the arc length, And so that was just the segment length, radius, and arc length. This is in radians. So the equivalent for velocity, linear velocity, equals the radius times the angular velocity. This is the formula we'll use, and we can substitute v over r for omega, and you can plug it right into this formula here to get the kinetic energy rotational. Alright, up here on the top we have kinetic energy of a rolling object, so I'm going to go ahead and do this calculation. So Ke rotational 1/2 I omega squared. So 1/2 of 3, that's a given right up there, 3. And omega is 20 squared. Complete the calculation, you get 600 joules. Here's a little more difficult problem. I didn't give you everything is listed. Determine the rotational energy of a car tire with each tire weighing 10 kilograms and the car traveling at 25 meters per second. Each tire has a diameter of 60 centimeters. So what we're going to do is get the kinetic energy per tire. Okay, well, and we're going to use the formula 1/2 I omega squared. And then we'll multiply that by 4 to get the overall for all 4 tires on the car. Alright, but what we don't have is I. That is not a given, as you can see up here. There are several formulas for rotational inertia of various objects. We are going to consider the car tire similar to a disc. Let me just draw a disc. So we got a disc here. So a disc has mass close to the center, mass further away. There is a formula, and I will write down that formula for rotational inertia of a disc, and it's 1/2 mr squared. All the formulas for rotational inertia have mr squared in it, and they just change out the fraction or what this number out front. But a tire can approach a disc because there is mass at the center, car tire. So I'm going to substitute that in, 1/2 mr squared. And then omega, like we said over here, omega is v over r. So I'm going to substitute that in, v over r squared. And notice we got r squared here. This will be r squared. So those will cancel, and we're going to end up with this formula, 1/4 mv squared. If you do the math, plug in the numbers, so it'll be 1/2. The mass of the tire is 10 kilograms. The velocity is 25. Square that. Whoops, this is going to be 1/4, not 1/2. And do all the math, and I think the correct answer is 1560 joules. And then you're going to times by 4 because we have 4 tires in this car. So total Ke would be 4 times 1560, which, let's see what that is. 4 times 1560, I get 624. I'm saying 6,240, and it is joules. Alright, let's move on. Potential energy, gravitational potential energy. Gravitational energy of an object is based on the position of the object relative to a 0 point. Near Earth, the 0 point is typically the Earth's surface, with the positive values above the Earth's surface and negative values below the Earth's surface. The formula, we're going to use the symbol of U, potential energy, and gravitational potential. There's different types of potential energy, but you will use U sub G, and then the formula is mg H. So we have an object. We got, well, this is ground level. We have an object above ground level, mass m, the distance is h, and we have the object in a gravitational field, so gravity is acting downward. So those are the variables that comprise this formula. So here's a situation or an example problem. We want to find out the gravitational potential energy of a rock. So just plug in U mgh, mass being 1, gravity on Earth is 9.8, the height is 20 meters. So you do the calculation, you get 196 joules. So fairly simple calculation. All right, finally, we have another type of potential energy, and that's potential energy elastic. Potential energy elastic is the amount of energy stored in a spring that is either stretched or compressed. The formula is similar. We have U sub S for spring, and it's same symbol for potential energy. The formula is not quite the same. 1/2 K spring constant, and the compression, the delta X, is squared. So this would be the stiffness of the spring. That's what I said right here. Measure the stiffness of the spring. Units are newtons per meter. Delta X is the amount of compression or elongation of the spring from its relaxed position. So there's the formula. In terms of an equation, or I'm sorry, in terms of a problem, we have the situation here on the right. A spring has a spring constant of 10 newtons per meter, and it's stretched 10 centimeters from its relaxed position. When I say relaxed position, I mean the position that it has no tension on it. That's relaxed position. So we'll go ahead and solve this. U sub S, 1/2, I'll write the formula down again, delta X squared. And then I just substitute in my values, K being 10 times delta X. Now this is in centimeters, so you got to convert to meters, which would be 0.1 squared. And if you go ahead and solve this one, I get a value of 0.05, and the energy unit again is joules. All right, that's all.